Yes. So we'll start with the concepts of the concepts of active, reactive, and apparent power. Apparent power. Okay. Now, the concept of active, reactive, and apparent power plays a major role in the electric power generation. The major topics we already discussed in this course was different generation technologies. So for any generation technology, there should be a generator. If it's a PV panel, then of course the technology for generation is different. It's not a moving machine, it's a static panel. But otherwise, the use of synchronous generators in power generation plays an important role. So in effect, the transmission of electrical energy and the behavior of AC machines in the sense here I refer to synchronous generators. And for wind technology, we use induction generators, right? So anyway, they are moving machines. So when power is injected to the grid, it flows from one part of the grid to another part of the grid. So both reactive power flow, active power flow, and apparent power flow, these things have to be properly dealt with. Now it is easy to understand when the flow is in terms of power rather than dealing with voltages and currents. So every time we need to deal with two waveforms if we are dealing with voltages and currents. Rather, if we deal with power, then we can directly go for power flow, and that is what is used by the load or the load demand, used as the load demand. So the terms active, reactive, and apparent power, they apply to steady state alternating current circuits, AC circuits basically, in which the voltages and currents are sinusoidal. Now, they cannot be used to describe transient state behavior, because in the transient state, whether if there is a switching or if there is a fault, then there will be a momentary interruption, and after that it will take some time to settle to the steady state value. So after settling down to the steady state, we can again see or analyze the sinusoidal waveform. So in the transient condition, we may not get a sinusoidal waveform. So we are not referring to transient states now. We are only dealing with steady state alternating current circuits. Now, we'll begin with an analysis on the instantaneous power in an AC circuit. So with an example, so it will be followed by the definition of power factor, power triangle, etc., which we have already gone through. I know that in some other course. So we'll start with an example. A sinusoidal voltage, I'm writing here, a sinusoidal voltage having a peak value of 162 volts and a frequency of 60 hertz is applied to the terminals of an AC motor. The resulting current has a peak value of 7.5 amps and lags 50 degree behind the voltage. Now we are going to answer some questions. The first question is, express the voltage and current current in terms of the electrical angle phi. Okay, so first we'll answer this question. Now I will ask you, if I want to represent, if I'm assuming that the voltage starts at 0, the voltage waveform starts at 0 and increases positively with time, and I'm going to represent, suppose E, the instantaneous voltage E, as some EM sin phi. In this case, what is EM? Anybody?
162.
162. So I'm going to write here 162 sin phi. So this is my representation of instantaneous voltage. Now I'm going to represent the current which lags behind this voltage by an angle 50 degree. So if I'm going to represent instantaneous current by small I, which is equal to some maximum current Im, how will I represent my sinusoidal function here? Sine of what?
5 minus 50.
5 minus 50 degree. 5 minus 50 degree. And what is my Im?
7.5 ampere.
7.5. 7.5. Right. Now we are slowly moving on to the second part of the question. Calculate the value of the instantaneous voltage and current at angle of 120 degree. How will I find it? I will substitute for phi 120 degree. Right. I will substitute for phi. Here I will substitute 120 degree. Here also I will substitute 120 degree. Then I'll get the E value. E value I am getting as, can somebody calculate this using a calculator? What's the value? What's the E value?
Sir, 140.3.
140.3 volts. Then I'm representing, then my current is, basically it's 7.5 into sine 70 degree. What is that?
Sir, 7.04.
7.05.
7.04, right? 04. Okay, 04 amps I'm representing. Okay. Now in the C part, I want to find the instantaneous power at 120 degree. Instantaneous power at 120 degree. How will I find this? How will I find this?
Sir, 140.3 into 7.04.
P equals EI equals 140.3 into 7.05 equals 989 watts. And I see that the sign is positive here. So what's the meaning of this positive sign for the power as per this question?
Power is being dissipated.
Dissipated means that is with reference to a point only. Here I have two things, right? I have an AC motor. It's evident from the question that I have an AC motor. So it means that it flows at this instant, because this is instantaneous power, right? At this instant it flows into the motor, right? The instantaneous power flows into the motor. Of course, motor is considered as a load here. So I am using this. Okay. Now in the D part, calculate the value of the instantaneous voltage and current. Calculate what the instantaneous power we have already found. Wait a minute. 1 minute. 1 minute. This is not okay. Let me. This is not calculate. Let me plot it. That's better. And you'll get a better idea. This is okay. Plot the curve of instantaneous power delivered to the motor. How will I plot it? The instantaneous power. So in this case, I am going to first draw the voltage and current waveform. If I am going to draw the voltage and current waveform, how will I draw it? Suppose my voltage waveform is like this. Okay, my voltage waveform is like this. How will my current waveform be? So it says that the current waveform is lagging the voltage waveform by 50 degree. So let 50 degree be here. Then what about the peak value of voltage? What about the peak value of voltage? 162 volts. And what about the peak value of current?
7.5.
7.5. Okay, so I'm drawing a current signal having a low magnitude and with a lagging. I have a lagging signal here. Okay, like this. Like this I'm drawing. Like this I'm drawing. Okay, so here this is my 50 degree. This is my 50 degree. This is my current waveform. This is my voltage waveform. Now, if I multiply these two, I will get my power waveform. So obviously, what about the magnitude then? It will be higher, right? So the crust and troughs, maybe the crust will be more. It will be higher when compared to the voltage and current waveforms. Now I am going to draw my power waveform. Okay, when I am drawing my power waveform, change the color. I'm getting like this. I'm getting a like this. I'm getting. This is my power waveform. So approximately, I'm writing the uh, peak. I'm representing the peak as plus 1000 watts. It's not 1000. It's actually what is the value? It was 989. Okay, approximately I'm uh, representing it by 1000. So now you can see that the power waveform has both negative and positive side. What does this mean? My instantaneous power. Okay, my instantaneous power. See, at a particular instant 120 degree, for angle 120 degree, I got it as positive 989 watts. But here I am taking the full waveform using the instantaneous power values. I am forming the power signal. When I am forming it, I get both negative and positive side. So what does this mean?
Sir, the phase difference between voltage and current waveform would be positive or negative.
That is one thing, but what about the power flow? Without
Sir, first,
touching voltage and current, how will you explain that?
sir, when power is positive, that means the power is flowing into the motor, and when power is negative, that means power is derived from the motor.
Okay, so I have two things here: power flowing into the motor and power flowing out of the motor. I'm getting two kinds of power in terms of direction. Now let us see what these powers into the motor and out of the motor represents with respect to active and reactive power. As of now, we have just multiplied V and I, and we have found the instantaneous power. Using the instantaneous power, we have drawn the signal and we just commented on it like this: the power flowing into the motor and power flowing out of the motor. And we know the period also, period at which power is flowing into the motor and period at which time period at which power is flowing out of the motor. And you can see from the signal that for very less time only power is flowing out of the motor, right? The direction is reversed only for a very less time, very short time period. Now the voltage, current and instantaneous power, when we plotted these things, the power attains a positive peak. We have seen that it happens at 1000 watts, and I have a negative peak also. So this is my positive peak. I have a negative peak also for power. Negative peak that is happening at maybe minus 218 watts. I can draw it if I substitute the phi value from 0 to 360 degree. If I substitute for E and I can draw the power waveform. If I do that, I'm getting the negative peak as minus 218 watts and the positive peak as 1000 watts. Okay, so the negative power means the power is actually flowing from the load, or here load is motor, from the motor to the source. So this occurs during at what interval? Here you can see 0 to 50 degree is the angle at which the power is flowing from the motor to the source, right? So from 0 to 50 degree, I have negative power. Now from 50 degree to where? 50 degree to, no, not from 50 degree. Let me see, 1 minute. Yeah, from 50 degree to which point? Here. What is the point here? What is the point here? If this is 0 and this is 180, this is 230, right? Isn't it?
Yes, sir.
230. So 50 to 230 degree, the power is positive. Okay, like that we can write. Okay, so although a power flow from a device is considered to be a load, this power is considered to be a load. We see that there is power flow from the source to the load and from the load to the source. This happens often in AC circuits. And the reason for this is the concepts of active and reactive power that we'll see. Now I'm taking another example where I have a generator or an AC source and I have a pure resistor. And my voltage is, I'm representing by E. Now my current is I. So, and one more thing before going to this, I'll mention one more thing here. I'm getting here, when I draw the power waveform, I'm getting here 1 by 120 seconds as my positive peak interval. This means that my frequency is, what is my frequency? 120 hertz for the power waveform. And for the voltage and current waveform, my frequency was 60 hertz. When I had drawn this using the instantaneous values, I got like this: 120 hertz is the frequency for power waveform and 60 hertz is the frequency of voltage and current waveforms, which means twice the frequency of the voltage and current that produce this particular power. Power has the frequency which is twice the frequency of voltage and current that produce this particular power. Now going to this pure resistive, yeah.
Sir, at 180 degrees, V equal to 0, then power equal to 0, sir.
1 minute, let me see. 180 degree. So at what all points we will get positive power then?
Sir, we will get 0 whenever I or V, anyone is 0.
Anyone is 0. That's all right. At those instants only, right?
Yes, sir.
Yeah. That is fine. So here maybe I have drawn in a different way. So at this point we have power should be 0, right? At this point 180 degree. So it should come like this. Is it like this? It should be like this, right? Isn't it?
Yes,
The
sir.
power waveform should be like this and it should go like this. This is
Yes.
again 230 degree. That is what when I had drawn this, there is a mistake. That is what. Okay. Now coming to the resistive circuit. Now we'll see active power. We will define active power. So what about the voltage and current waveform here? What about the voltage and current waveform here? Can anybody tell me? Suppose my voltage waveform is like this, then my current waveform, of course the magnitude is different, so I'm getting an in phase waveform, right? I'm getting an in phase waveform. So this I am representing this by capital E, which is ERMS. Okay, capital E, which is ERMS. Now this is my capital I, which is IRMS. Okay, now what should be my peak? What should be my peak current then? Anybody?
EI.
I into? Right, I into √2. My here my E into √2 should be my peak voltage. So here I'm seeing an AC voltage E, which produces an AC current I in a pure resistive circuit, and hence they are in phase. So if I am connecting a wattmeter here, if I am connecting a wattmeter in this line between the pure resistive load and the generator, the wattmeter will read watt power. What should be the power here? What is read by the
E square by R.
V square by R.
No, it's V square by R, but what you have here is ERMS into IRMS, right? ERMS into IRMS. If you want to take V squared by R, you need to take the voltage across resistor, and if there is a drop here, suppose if there is a drop here, then after accounting for this drop, you have to take the voltage across this. Suppose this is a if the resistance is neglected and if it is 0, then of course it is E squared by R, or with respect to current and voltage, as the wattmeter is installed in this line, it senses the voltage and current and it calculates the power as E into I. Now here in this case, if I try to plot the power waveform, then how will I get the power waveform? Whether it will have a negative part, whether it will have a negative part. Anybody?
No, sir. No, sir.
So how will it look like? If I draw like this, after this point, what will happen?
Sir, same thing above. Same thing.
It will repeat, right? This crust will repeat like this. Will repeat like this, right? See, these are equal. Okay. Okay. Now, so what is this peak value? What is this peak value?
2 VI, 2 EI.
Yes, 2 EI. Good. 2 EI. So 2 EI is my peak power value. I am getting only positive direction, which means that here in this case, power is always flowing. The direction of power is such that it is always flowing from the source to the load. Now, this is what is the concept of active power. The fact that the power is always positive reveals that it always flows from the generator to the resistor, This is one of the basic properties of what is called active power. Active power. Okay, so although it pulsates between 0 and maximum here. See, from 0 and maximum it pulsates, right? But it does not go to the negative side. Now, how will I calculate the average power from here? How will I calculate the average power? The average power is clearly midway between 2p and 0. Okay, 2p and 0. What is 2p here? Root 2e into root 2i, which gives me 2 into ei. Ei I am representing as p, which is equal to 2p. Okay, 2p. So my average power is clearly midway between 2p and 0. So its value is, average power value is p equals 2 ei divided by 2, which is equal to ei watts. So it's a constant, right? It's a constant. So at ei, I am getting a constant value, which is the average power. Average power. Now, there are two conductors shown here, right? How will you represent the current flow in these two conductors normally? The two conductors leading from the generator to the resistor is carrying some current, means normally we take it as a loop current, right? So one conductor carries current in one direction and the other conductor will carry current in the other direction. It's a return path, right? But unlike the current flow, the power does not flow down one conductor and return to the other. Power flows over both the conductors. So that is why we can represent power flow by a single line also, like this. Like this. Okay, so it is carried by both the conductors from the source to the load. The direction is what matters. Either it is from the load to the source or from the source to the load. Here it is from the source to the load. Okay, because it's purely active. Now, the generator is an active source and the resistor is an active load, right? We call a generator as an active source in this case, and the resistor is an active load. As of now, the generator is not generating or delivering any reactive power Q. So that is why we call it as an active source. The symbol for active power is, as you know, it is P, and the unit is watts, and it can be in kilowatts or megawatts also, right? Now coming to reactive power. So to represent reactive power, I am drawing here a generator connected to a pure reactive load. So I am representing it by an inductor and a complex reactance J into XL. How will I draw my waveform in this case? So this circuit is identical to the resistive circuit, except that the resistor is now replaced by a reactor. That's all. As a result, the current lags. Current is this. Suppose my current is this. I'm drawing like this. Okay. My current lags the voltage. My current lags the voltage. So how will I represent by a waveform? What really goes on in such a circuit? We'll see what really goes on in such a circuit. So here, suppose this be my voltage. Okay. How will I draw my current here in this case? Where should I mark? Where should I mark? Where will be the current 0?
Pi by 2.
90 degree.
So where should I mark?
Sir, just below the peak.
Just below the peak. So I'm drawing it here. Okay. Now my current waveform is, you just see whether it is right or not. Is it right?
Yes,
Is it
sir.
right? Yeah. Yeah. So here, no, in this case it lags or lead.
Current lags.
That is what, 1 minute. E I. How will I draw my P in this case? I'll take another color. Where will be my power 0? Where will be my power 0?
N pi by 2.
So in that
Yes,
case,
sir. I bet.
so from here, it will start to the negative side or positive side?
Negative side.
Negative side, good. Now, where will be my power 0? Here, right?
Pi
Here
by
or here?
2.
Here or here? Here, okay, 1 minute. Is it like this? Is it right?
Yes,
Yes,
sir.
sir.
Yeah. So it will go like this. Now, if this is my power, here you can see both positive power values and negative power values. So the power P consists of a series of identical positive and negative pulses. The positive waves correspond to instantaneous power delivered by the generator to the reactor. Here the load is reactor, and the negative waves represent instantaneous power delivered by the load to the source. So the duration of each wave corresponds to 1/4 of a cycle. Pi by 2, right? 1/4 of a cycle of the line frequency. So the frequency of the power wave is therefore again twice the line frequency. In this case also, frequency of power wave is again twice the line frequency. Now, basically what we see here is the power that surges back and forth, right, which is represented as reactive power. Power that surges back and forth, reactive power. The symbol is Q. Symbol is Q. So to distinguish it from the unidirectional active power mentioned before, here this power surges back and forth. Now, the reactive power is also given by capital E into capital I in this case. Only thing is its direction is, alternating. Now, but by the unit VAR, we differentiate it with respect to active power, right? Active power. Now, with respect to vector, how will you represent reactive power with respect to vector? If I keep a var meter, see previously I was keeping a watt meter, right? Here a watt meter. Instead of that, I'm keeping a var meter here, and I just want to uh, measure my reactive power only. I don't want active power. I just want to measure reactive power only. Then what should be the calculation? A var meter registers the product of effective line voltage times the effective line current, or the ERMS into IRMS, times what? ERMS into IRMS times sine theta, where theta is the phase angle between E and I. See, this EI is in this case only because we don't have any. This is 90°, right? Theta is 90°. So that is why here the pulsating power, which is equivalent to the reactive power, it is found by EI. But in general, for a load which is an impedance which has both X and R, if you want to find the VAR using a VAR meter or a VAR meter, then you should calculate ERMS into IRMS into sine theta. So this is what is the concept of active and reactive power. 1 minute. Let me stop the recording.